Good morning, my QSR friends and colleagues, and my name is Kamran Peinavar. I'm current chair of Quality Statistics and Reliability section of QSR. As you know, today here we gathered to celebrate the 20th birthday of QSR. On behalf of the organizing committee, Kaibo Liu, Kaibo Wang, Hao Yan, and myself, I would like to welcome all of you and thank you for your support. I don't want to make any speeches or something like that, but just before we start with the workshop, I want to acknowledge our sponsors who generously supported the workshop. Penn State, University of Michigan, Georgia Tech, University of Wisconsin-Madison, Hong Kong University of Science and Technology. I appreciate your support. Without further ado, I turn it over to Professor Shi Zhu to start the first session. Please put your hands together and welcome.
Good morning, everyone. Today we are very happy to have Professor Jianjun Shi to give us the first keynote speak to kick off this workshop. I think everyone knows Jianjun Shi, but I still want to give a brief introduction of his background. Yeah, Professor Shi right now is a Carolyn and Stewart chair and professor at the Department of Industrial and System Engineering at Georgia Tech. And Professor Shi is a pioneer in development and application of data-enabled manufacturing. So his methodology integrates system informatics, advanced statistics, and control theory to solve design and manufacturing problems. And his research have generated a very large number of well-cited engineering literature. But on the other hand, his method also being applied in practice generated a significant economic impact. For example, his version reduction technique has been applied in more than 20 plants in automotive industry. And his data fusion methodology has been implemented in more than 40 steelmaking companies. So really significant economic impact. And Professor Shi has received more than 18 million research grants and various awards and distinctions. For example, he has received this David Baker Distinguished Research Award from IISE and this Albert Bozeman Distinguished Educator Award from IISE. Right now, he's a fellow of Informs, IISE and ASME. And this year, he was elected to National Academy of Engineering, the highest honor an engineer can receive. And Professor Shi is the founding director for QSR session. Start from beginning, this Professor Shi contributed critically to the establishment and development of QSR session. Let's welcome Professor Shi to give the keynote speak on evolution of data fusion methodology.
Thank you. Yeah, thanks, Shi. And thanks for inviting me to come here. It's really a pleasure for the 20 years anniversary. How to do it? Yeah, I'm really happy to come here for this 20 years anniversary events. So in this morning, I was asked to give the first talk, and then ask a few friends, say what I should talk. This is really not like a research presentation. So we talk about the history of QSR as 20 years anniversary, and also I'm thinking maybe I should look it back, talk about the evolution for data fusion for quality improvements, which is something I have been doing for years. And also we say 20 years anniversary, really it start 22 years because we need 2 years test period for QSR for invited session. And after 2 years, we demonstrate there are sufficient session stability, and then the board will approve the QSR session. So really we talk the 22 years history of QSR. So my talk also started 22 years ago when I joined faculty in IOE. So when I talk about the evolution of data fusion, I think I like to emphasize for research problems, where it come from, what's the motivation, why this becomes important research problem, and the motivation part. I think when we're doing research, really two aspects very important, maybe more than two. But the first one is identify real problem, important problem, and this one really have potential impact. And then we try to find the best technique, methodologies to solve the problem, give the best solution possible, and then try to implement this one in reality, and also try to introduce this to others so more people can work on this one. In my mind, those are the important steps. But very important one is first one. Why we work on this one? Why this is an important problem? So that will be my focus of this talk. So in this one, I talk about the concepts, data fusion for IPQI or data fusion research. And then talk about the evolution of data fusion research over the years. Really two main streams. One is a signature analysis from a single functional curve to multi-dimensional functional curve to high-dimensional streaming data. So that's the first line. The second line is stream variation modeling analysis for multi-stage system. And then very briefly say what future topics could be. So talking about data fusion is always associated with product realization. So for any product, this for engineering design, manufacturing product, or even service product, they always go through the following major steps. The first one is define the need from the market, why we need the product. And then we design the product and engineer specifications, how many components, and then design the manufacturing process, how to fabricate the product. And then put into production on the floor and produce product, quality inspection, and also need supply chain logistics to link those different factory, different departments together. And also customer service, once customer get the product, how to make service, maintenance, and so on. So in this product realization cycle, in each step, they generate lots of data. And from this lot of data and model in practice, the data has been used very well in each own individual steps. However, they are not interrelated between different steps. The data fusion idea is try to get the data, the model from each step, and transfer raw data to information, knowledge, and make the best decision. And then go back to impact on those individual steps and make the system overall better. In order to do a good data fusion research, we need three pillars. So first, we should understand the domain knowledge. Whatever we're working on, we should have engineering, physics, domain knowledge. And then we should understand the data science. Here I refer to like statistics, computer science, machine learning, signal processing, video processing, basically the data side. And then we need to know the optimization, control, how to do a better job. So only these three pillars work together, we can do a good job in the data fusion for quality improvements. This is a slide in 1995 where I interviewed in Michigan. Some of older friends know my training. My academic training was in EE with focus on automation. I got my bachelor, master, almost PhD in China. And then 1989, I went to Michigan in mechanical engineering, got my PhD in 92. And then stayed 3 years as a research scientist in mechanical engineering. So I never been in IE before. So 1995, I got an offer, job offer to join IOE in Michigan. So I'm thinking, how can I contribute to IE? So I need to learn IE and then think how to contribute. I belong to this quality control group in IOE. So I try to understand what's the quality engineering in that time. So if we say this is the manufacturing process briefly, so we have designed the product process, manufacturing, fabrication, get the product inspection, and then ship to the customer. So this is the flow. So in that time, I say there are different methodologies well developed. One is the design experiments. So basically how to design the product process robust to the product disturbance. And also there are SPC, how to do sampling, process control monitoring, and so on. And another one is the quality management. to coordinate different aspects from management point of view. So I'm looking at this slide. I mean, looking at this different existing quality control methodology, I think I found there's opportunity, which is in-process quality improvements. Why we say this is very important? Because if we have the best design experiments, make the process robust to the disturbance, something may happen during the manufacturing process, which cannot be anticipated. And then the defects may occur. Another thing, SPC, we do the sampling, measure the product, and see in control, out of control. But if something out of control, something defects are already made, bad happens. The management can do the training, do the different aspects, but cannot guarantee something not happen during the manufacturing. From another side, there are lots of sensors during the fabrication, during the manufacturing, in line. And also the intermediate product can be measured in the manufacturing process. So if we can do real-time defect prevention during the stage of manufacturing, we can get quality control to another level. So if we compare different tasks in the quality control, say process fault, the SPC emphasizes fault detection. What we like to do is not only detection, but also isolation and identification. And also talk about defects. The conventional SPC emphasizes inspection. And what we like to do, I hope, is the prevention. No defects occur in the manufacturing process. And also how to solve the problem resolution. The conventional quality control emphasizes in control, out of control. Once out of control, they need operator to close the loop. Is the offline operator intervention. And we like to have a systematic approach to do this. So, like here indicated, for conventional SPC, emphasize product inspection, sampling, design SPC control charts, out of control, closed loop to change the process by operator. What we like to do is, in addition to the product measurements, we also measure in-process sensing, which is process variable and the intermediate quality variables. And based on the engineering knowledge, statistical analysis, through optimization, we can automatically find what are the root cause problem, how to resolve the problem, and more importantly, how to do compensation control. So in this way, we can reduce and eliminate these defects. So these aspects, we call the data fusion. So the data come from process variable, quality variable, engineering design, and all together make a better decision or data-enabled design manufacturing. So from here, start the first stream, functional data analysis. And this one is, okay. First one, talk about the signature analysis for high-dimensional streaming data analysis, analytics. Like I said, in this presentation, I emphasize motivation, why this is important in that time. This particular work was started like 1995, working on this. So this one is the stamping press. And the blank coming in, formed parts, we get this particular foam stamped parts. The typical quality control will sample this product, and then to see what the dimension, the surface condition, and so on. So if something wrong, if something wrong here, the watch stopped, so I can talk forever. Okay, if something wrong, they try to figure out what the manufacturing process, how to reduce or eliminate the defects. The drawback of this technique is there are more than 40 variables, material property, setting, die setting, press parameters can impact on this quality. If something wrong already, what are the root cause? How to solve the problem? It depends on who is working on this one, who is the engineer. From another aspect, there are lots of sensors already installed in this stamping press. For 280 tons press, they can have up to 150 vibration sensors. Lots of die tonnage sensors, like here. the height, the speed, and so on. So each time they puncture part, they generate a curve. This is an example of tunnel signal. So from here, the upper die going down, touch the lower die, start form the parts, force increase. And then this going up, this force going down, and here become 0. That's the departure. So this is one cycle corresponding to one punch, one part. And different segments of this curve corresponding to different mechanical interactions, different forming stages. Use in other words, if one segment has some problems, changed, that's corresponding to something wrong in the manufacturing process. And the different segments have different potential failure. So we said early, engineer domain knowledge, data analysis, and optimization. So as an example, the tunnel signal here can be divided into 8 different segments. For each segment here, there are some potential faults may occur. And for each fault occurs, they have corresponding frequency and magnitude change of this one. Here, just some examples, see different segments, what happen. So after we have this kind of knowledge, the signal, the engineer domain knowledge, what could be the best technique to address this problem? So we used wavelet analysis. So basically, we use from the functional curve, transfer to wavelet coefficients domain, and also from engineering knowledge, we know different sections have different potential interesting features. And then we do a mapping between these two. And then we can see for certain segments corresponding to certain faults, certain particular coefficients in frequency domain or time domain can corresponding to this. So by using this kind of decomposition technique, we can do best feature extractions for different purposes, monitoring root cause diagnosis, the die setup. So that's we can do. So that was the motivation, the techniques to solve this problem. So right now, I talked one functional curve on one sensor. They have each column has one, can have up to 8 sensors. So the interrelationship between these functional curves also makes sense. So that's like starting of this one. If you think about, right now I'm talking about this one is a tunnel signal. But in fact, this is applicable to all cyclic signals. So this one, like if you drill a hole, you get a fault like this. You do a welding, you get something like this. Our heartbeat is something like this. If this one heartbeat, they have different segments corresponding to different components, different cycle. And then you can monitor what segment change. You can do diagnosis, monitoring, and so on. So the concept is really applicable to different things. So this is like a starting point. This one is a recent project. Nanobaki paper process scale up. This one is also functional data analysis, but different from before. So first, what's a nanobaki paper? Nanobaki paper is the nanotubes, like my finger nanotubes, aligned perfect. If aligned perfect, like this way, along this direction, the mechanical property, electricity, heat transfer had very nice property. If normally it's cluttered, but aligned this one. Before we work on the project, that was 4 years ago, they can only make Baki paper one at a time, like a piece, one piece, and then another piece, just like regular paper we have. So what they like to do from the user, Army, Navy, and user, they want to have a row-to-row manufacturing. In other words, instead of one piece of paper, they continue production like toilet paper, much wider. Okay, so row-to-row manufacturing. So for the row-to-row manufacturing, they have that kind of manufacturing process. But one problem very critical is variation monitoring, variation reduction, and the first step is how to monitor the quality. So we use Raman inspection to measure the quality in the end of the line. And in fact, in this row-to-row manufacturing, we measure different zoom. Okay, it's not one point. Just like if this is one section I should measure here, 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 here. Okay, this different point. Each point, my finger touch here is not a one point. It's multiple points here. One touch, another touch, multiple points. I'm not only measure this production, but also continue to roll. I need to measure here, 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 and so on. So this spatial temporal within a zone and globally. And then if every signal, this curve, is absolutely repeatable, that means my quality is very stable. It could be unstable between this touch, this touch, this touch, could be over time different. So the question is how to monitor it. So for this problem, we have multiple features we care about from this Raman data. The D zone, B zone, the ratio. If here in the middle, there's another peak come out, so that means there's contamination. Some other things not wanted show up in this one. So we need to monitor these multiple features with multiple functional curves. So how to do this one simultaneously? We propose this decomposition technique. I just quickly go over this, see if I can explain clearly. This Yij here is this functional curve. And this Yij. And this mu I is a fixed effect, is a group of multiple curves, take an average. I got this one. This one corresponding to, I said, one touch, two touch. Each touch, I have one mean value, multiple functional curves. This W is a basis. We use wavelet basis. And theta ij is coefficients. Try to get this together. I mean, W theta ij is the mapping of this functional curve. Sorry, here should have an epsilon. I mean, Eij here. I mean, not sure. Oh, here. Okay. Okay, after this one, this W delta ij is something anomaly. Use in other words, if something there's a peak show up and cannot be, mean value, this one try to fix this curve, but the theta ij will be bounded. And how large this bound is the natural tolerance we specified for this production line. Use in other words, within this range, the production will be good. So we try to estimate theta ij, delta ij to minimize this curve. And then if mu ij, wij, we estimate wij, we can get a good fit of Yij. We don't have any defects, delta ij. That means no peaks occurs in the middle. If I used up this tolerance and the mu I and W theta I fit this one, still something left. The something left would be a peak here somewhere. And then delta Ij will be non-zero. So we have defects occurred. And the Eij is the noise. So through this, solve this optimization constraint optimization problem, and with the penalty to say cannot be too many outliers here, we can accomplish one-step decomposition from the Raman spectrum to between different touch, the mean difference, normal effects. If within a touch, different curve, do they have similar? And if there's outliers for each curve, this defects and the noise. So by using this optimization, we got these three features. Monitor these three features, we can accomplish monitoring the production line. Okay. So this is talking about multiple functional curve, multiple features. This another ongoing project is with Samsung. So Samsung contacted me for chamber monitoring. For each chamber, they have 130 sensors. Each sensor has a functional curve, like this. Before work with us, the Samsung practice is monitor each curve by adding an upper-lower bound of this curve. And then if this curve go beyond this upper-lower bound, like this auto control, something changed. So this is their practice. And they are not happy with this result. They said, okay, they know in certain segments, some multivariate will interact. And the interaction change also means something. So can we use multivariate monitoring to monitor a cluster of functional curves simultaneously? We can get a better detection means something could not detected, can detect. Something can shorten the detection time if something occurred. So that's the desire. However, in order to do multi-variable monitoring, we need to know among 130 sensors, which sensor is a cluster correlated. If you don't know which one correlated, you cannot do it. Okay, first. Second, another challenge for the semiconductor problem is from the beginning here, for example, from here to the end, is one wafer get in processing. The process is not do one thing. They do 50 to 80 different steps depending on the recipe. Use in other words, if there's a functional curve from here to here, there are multiple steps. The first step, say deposition something, do the cleaning. Next step, deposition something else, and do the cleaning. So you can see this functional curve divided into multiple steps. That's one thing. The second thing is that each step, when they start, when they finish, when next start, is not fixed. They have a fixed feedback control inside. So use in other words, the first step for the first wafer stop here. The next one may be here. Next may be here. So there are multiple steps. The segments is not clean cut. You cannot preset. So the curve you get, multifunctional curve, is something like this. I mean, this is just a subset of this. So here's the challenge. We don't know when this step finish for a given step. And also for this particular step, we do not know which functional curves are related. If so, how can we do multivariate monitoring? So we get stuck for a while. And later, Chen Zhang and Hao Yan, they come up a technique. Okay, I say technique later. Here's the problem, again. This is multifunctional data. What we like to do, objective. One is automatic time segmentation. Okay, get the segments automatically. The second one is automatic subspace identification. So subspace, where they are. I mean, which one is clustered and correlated. Okay, this is something. After we get this one, we know when they stop, we know the cluster, and then we can go back to the conventional technique we're familiar with to do the monitoring, feature extraction. So very briefly, what's the concept we did? So there are multiple functional curves, and also we assume some of them clustered like this. For the same clustered one, they have a similar, they have same basis, basically. And the way we learn the subspace is try to do self-exploration, self-regression. The idea is like this. If I look at my finger here, I have 5. Okay, I have 5. So, no surprise, I have 5. Okay, so I have 5 functional curves. And I tell you, before I do anything, these 3 are correlated, clustered. These 2 are clustered. So this one is given. But in reality, you don't know. So what we are doing is, I use this one as a response, regression on other 4. So if this was response, regression on other 4, we can anticipate these 2 coefficients will be larger. These 2 will be small. We cannot say it's 0 or big, but essentially like this. And then I use this one as a response. The other 4 as a regression, these 2 will be large, this will be small. And then if I use this one as a response, this will be large, these 3 will be small. So basically, I go one by one as a response, regression on others. I will get this map. So this is the first one's response, second one, and the coefficients are large. Okay, get this one. And then regroup this one, get 3 clusters. Use, in other words, each cluster is a subspace for this. Okay, this is one idea. And another idea is we allow these coefficients time varying change. So we do a regression. It's the same as before. But also we say these segments cannot be too many. You cannot change all the time, otherwise it will be overfit. So we get Bij t minus 1, these coefficients here have a penalty, absolute value here, 1 norm. With this penalty and also allow this t change, we do 2 things simultaneously. Do the optimization. One is font segmentation which is when this this coefficient changed. Another one is clustering. So this one is corresponding to one case study, one example to show the beginning t equal to 32 step, t equal 60, t equal 120. You can see the clusters evolving over time and changing. This particular example is really come from this one. This is a person, this is a public data set from website. This is a person ball, and then ball pick up something, and then throw away. So you can see in this particular task, there are two tasks. One is the ball going down. And what's the data you just see? The data is every joint here. They have a recorder to show X, Y, Z position of this joint. So if I move this one, my two hands, the joints, will move together. And if I throw away the three joints here, we move together. So basically you can see from this data set, we can automatically cluster the joints. So the same color belongs to same clustering. So this same dark blue and so on. So you can see this one. And then by this point, they finish the ball task. This one starts next task, the throw away something. So you can also see the blue colored one cluster, these three red colors are another cluster. So you can see the data I got is the person stand up, start to ball, and finish draw. So basically I got one function curve. I don't know what is it. By using this technique, I can segmentation to two segments, and each segment, which cluster of data is related. So that's for this work. In fact, the reason we work on this data is motivation come from Samsung's request, multivariate monitoring for functional data. We need to learn segmentation. We need to know the clustering. So after a while, struggle, Chen Zhang, Hao Yan developed an algorithm, work very effectively, very nice for Samsung. And Samsung liked it so much, they said, Jian, don't publish it. You cannot publish this one. And this semiconductor process, these very innovative ideas, we want to keep it. So I feel very bad because for students, paper very important. For me, relatively less important. So later on, Mustafa recommended this data set. We look at the data set. That's exactly what we need. Multiple segments, different tasks in the middle. So we use this one, publish the work, and it's okay. This has nothing to do with Samsung. Okay. So earlier I said different functional curve. One functional, multivariate, hundreds of them. So go even further is high-dimensional streaming data. So this is a high-dimensional, the image is high-dimensional. This continuous video record, video signal is high-dimensional. So anomaly detection for this is also a very challenging problem because the high dimension, lots of pixels, lots of, like in this, 0.01 seconds, one dot, and then 20 minutes, 25 minutes, one circle. So lots of data. High velocity, come very fast. Complete special temporal structures. And more importantly, the anomaly here, we don't know when this occurs. We don't know where the location on this image or curve, and we don't know the shape beforehand. So we don't have this information. The question is, can we do unsupervised feature extraction from high-dimensional data for anomaly detection? And we emphasize unsupervised technique because if we want to do supervised, we should have several conditions. One, we should have the defects. Two, we should mark the defects and the normal. And all this one is time-consuming plus. You cannot have all types of defects. Impossible. So that's the unsupervised, always preferred if we can do it. And also, the process data is very easy to get. Continuous production, continuous data collection. Some of them good, some of them bad. Very few of them bad. So that's the idea. So how we do it is to do one-step decomposition. So the idea is from the high streaming data, the real data, they have a smooth background, and they have sparse defects, and then they have noise. If we don't have any new technique, just learn the textbook material, signal processing, video, image processing, what we will do is from this raw data, we do denoising. After remove the noise, we do the feature extraction. So that's a typical way we do it. We do this has two drawbacks. One is when we do the denoising, two steps. First step, denoising, some small defects anomaly already smoothed out. That's one problem. The second problem is for the defects and anomaly, if we do the denoising, the boundary of this one will be blurred for these defects. So that also reduces the detectability and classification accuracy. So the way this how YANs work. The way is how did is we do one-step decomposition. So basically, assume that for the background, we have a temporal spatial basis. And for anomaly, we have a temporal spatial basis. And then the original signal will be decomposed as there's a tensor estimate theta here, estimate theta and theta A to do the detection. In this particular work, there are two contributions. One is formalize this kind of problem into this optimization format. The second one is how to do quick computation algorithm to solve this quickly and recursively. So that's two aspects. I don't show the algorithm, I show some demo. This is a simulation result. Here is original, the simulated measurement with noise. This one is a background. There's no anomaly, nothing here. When there have an anomaly, this one will immediately show up, the decomposition. And here has an alarm sent out. And in the rolling application, this continuous video signal, this estimated background, no defects occurred at this time. Once there's a defects occur in the video, here show up some defects detected, and here alarm sent out. So this is another example. So right now I finished the first topic is functional data, multi-high dimensional data, image data. And so far, I talked about monitoring, anomaly detection, but not quality improvements yet. So if we want improve quality, we need close the loop between quality defects, anomaly, with the process variable. And when I go to plant, talk to people, I always say this: do you want to improve quality? Of course, yes. And then, can you give me data, the quality data synchronized with the process data? I can help you. Because in any plant, they have automation, they have feedback. So the sensing signal already there, but there's no relationship between the process variable automation signal with part quality. The signal will be used to control the speed to 1,000 RPM, the pressure to this pressure. But how this is related with quality, this is not something common in practice. And this is something our IE people can do. We do the system level, we do sensor analysis, and so on. So here's the example. But people say, right now the machine learning, deep learning is so good. I have so many data. I get a computer science guy. I put the data dump to them. And without you guys, we can get a model, we know everything. I said this will never work because we work on engineers. I'm not talking about weather condition, others, economy. I'm talking about the engineer, the manufacturing system. So engineer manufacturing system is a designed system. So there are certain engineer principles there already. So by using engineering principle plus the data, we can get much better result than just the machine learning, deep learning, and so on. So we emphasize physics-driven machine learning modeling for manufacturing data. So normally I say manufacturing system like this. System network is hardware. Each machine has sensors. And from the product process design, we can have data. From the manufacturing process, we can have data. And then based on the physical network, we have sensor network and determine the final decision network. So this is the way work together can make the system better. And by developing this one, we can link the quality information with the process variables. And one motivation example, illustration, is a rolling process. So we measure the rolling quality in real time. And also there are 50 or hundreds roller stations. We know what the sensor system layout. And we know which variable corresponds to which station, which quality measure corresponds to which stage of this one. So we can have, without learning, without data from the engineer design, we can have some kind of initial network. And based on this network, with the data, we can develop causation-based process monitoring diagnosis control. And we implement this one in rolling process, get that kind of network, the quality, process variable, and the model can be multiple purpose to use. For example, if I know the machine setting, the process variables, I can predict the quality with probability. If I know something wrong, I can go back, trace what could be the root cause. And also, if I give for given material, for some variables like speed, I can change as a control variable. By changing this one, I can get less defects, avoid defects. So this one is causation-based quality control. Okay. I briefly mentioned second topic is variation reduction for automotive assembly process. Okay. I say a few words, 2 millimeter program. 2 millimeter program is a car. For a car, you have 130 measurement points, critical dimensions. Each critical dimension variation smaller than 2 millimeter, that is world-class quality. In that time, late 80s, that's Japanese quality. USA, in that time, 6 millimeter. So reduced variability is a motivation to do this work. So again, talking about motivation, why we work on this one. For a given car, late 80s, Perceptron introduced these inline measurements. This one, shoot on the car, can get XYZ dimension, and 130 cameras over there. So when factory implement these perception sensors, laser sensors, they get 130 times 3-dimension data. The technique they use has been X bar chart, R chart. So right now they apply hundreds of control charts on this sensor in that time. What consequence? Always something auto control for sure. And the training in that time, the quality control training, if you know the process auto control, you should shut down the line, fix the problem, and then restart the line. That's the training. So basically, they cannot run production by using so many sensors, the conventional technique. That's the reason my advisor, Sam Wu, lead us in that time, started variation reduction, how to use this data effectively. So you can see, more data is good, but more data makes the production cannot run without better methodology. So we start with saying how to use this effectively. We use principal components as a data visualization technique. So you can see this M is measurement points. By using, after you get this data, we can calculate the first principal components. The eigenvector, the magnitude, the sign, will have that kind of drawing the direction, which basically shows the parts rotate, move, that kind of thing. So we make a program to GM, and GM really likes this. So make a program, all plants using this software to see this. And in 93, 94 time period, GM chief technician, a statistician, said there's no proof this measurement data used PCA get eigenvectors is corresponding to the mechanical failure or the dimensional failure in the system. There's no theoretical move. So the send a note to all plants, stop, use this report. So afterwards, we say we have to, in our deep heart, we think there's a relationship. So afterwards, Derek Sigleric and I, we did some study, use engineering design. We know the location of the locating pin, the location of the measurement points. For each potential failure, the parts, for example, if this failure, the parts will rotate along this axis. So How many? 3. Take 8. Okay, so this, we will have a break, right?
Yeah.
Can we delay 5 minutes? Okay. So when this rotate, from the geometric relationship, we can get variation and the distance relationship. From the measurement data, we can get covariance matrix and eigenvalue eigenvectors. And we proved if the this fault occurs, this diagnostic vector from the geometric design is the same as the first print components. I mean, we have paper prove this. So after we prove this one, we show the GM, the statistician. He said, okay, right now you can use it. So that's but the nice part is with this kind of proof, offline, we can have, from the design, we can have all the potential faults. And online, we have the data. I can get the first eigenvector. And then I can do a mapping here. So I can find out which one has the error. So this, I say, engineer design potential ones with real-time data analysis and the mapping solve problem. So that's the data fusion idea. So we did some analysis, and later on we say, okay, we can monitor the data, we can do the clustering and so on, but we don't have unified methodology to handle variation reduction. And we want unified methodology, so we propose this stream variation for multi-stage manufacturing process. So what common things for multi-stage manufacturing process? You can see car, multi-station assembly, get final car. The 3D printing from layer after layer is also multi-stage. Machining, semiconductor, all multi-stage. So for multi-stage problem, what things in common? Assume these two parts assemble, part has a dimensional problem or a fixture problem. This one will assemble not perfect. The error will propagate to the last station. So there's a variation propagation problem. And also, we want final product within certain tolerance. What tolerance should be given to the parts and the tooling in each stage? So that's a tolerance synthesis problem. Something wrong in the final product. What are the root cause? Diagnosis problem. I want guarantee my monitor process which station measure which feature is a distributed sensing problem. And along the production line, which station is more sensitive to the final quality? Critical station identification. Something wrong in one assembly station, not perfect already. Can I do something compensation to make final product not so bad? Automatic compensation problem. So those problems are applicable to any multi-stage manufacturing process. So talking about this one, what are the unified methodology? What's common? We should link the data in 3 dimensions. One is a multi-stage. Another one, these are attributes, how many qualitative attributes. This over time. If we can model the autocorrelation along this axis over time and cross-correlation between them, we have a good understanding of all the features. So how to do this? How to get the model? So we propose this state-space model idea. So at stage K, some features are already made. The quality feature xk minus 1. After stage K, xk, this quality output. In stage, we do something on the parts, uk. There are some natural tolerance on the parts, that's wk. If some fault occur, wk not the right distribution, okay? And we may measure some features in this station. So we can, for each station K, we find the relationship, incoming quality, output quality, additional tasks, work on this one to the output quality from K to 1 to N. We can get a quality propagation model. And then take covariance on both sides, here's a variation propagation model. We can measure some xk by using ck, and then we can get observation equation model. And how to place ck components? If all 0, I measure nothing. If I measure something, put something 1 or half is a combination of quality features. So that's how we do this one. If we look this model, if you learn linear system control theory, this one is linear system equation. So some concepts, ideas can be borrowed from there. However, there is a fundamental difference. K here is the stage number, and stage is delimited, 1 to 50, 1 to 100. For a linear system, control theory, K is time, go to infinity. So all the definitions of stability, observability, and so on need to be revisited to get something for us. So by using this systems model, we really link the manufacturing process control with system control theory, with multivariate statistics, and this one set up foundation for this. And over the years, we have been working on this one, continues to improve quality, this up to 10 years ago. Continues improve the modeling by considering more and more factors, how to do manufacturing, process monitoring, diagnosis, compensation, and how to improve design of the product and the process and the tooling and so on. So when I say a unified methodology, unified model, this is what I mean. By using this state model, we can do different aspects from design and manufacturing. Currently, I have ongoing projects with the Boeing company on Boeing 787, use this concept to do better design, better control. So for data fusion research, we say what's a research methodology or concept research? I think in this way, we should always identify a real problem. Real problem, important problem, like a variation, like all the examples I say, they are real problem. No matter we can solve it or not, it's a problem. So if real problem cannot be solved, must need some fundamental research. After we have some fundamental research, we need to have enabling techniques, methodologies, software, prototype, and then try out in reality. So may or may not work. Some will work, some does not work. Does not work means new methodology needed, new enabling technique, and then new broad implementations. And also, in order to make this have impact, we should have education component. So the master student can learn this one and hopefully can contribute in practice. So the data fusion research, if we say what could be more opportunities, there are lots of new opportunities, cyber physics system, IoT, smart, automated, lots of 3D printing and so on. No matter what kind of manufacturing system, is follow the same process, like in the beginning, a big circle. So design, product design, process design, and so on. So they follow different steps. And currently, by using a better data acquisition, we have a higher dimensional data, dynamic data, heterogeneous, so those kind of things. And then by using better data analysis techniques, machine learning, artificial intelligence, and so on, we can do better for design, manufacturing, decision making for quality improvements. I think this is my last slide. Exactly 5 minutes more. I'm fine.
So you have done this work from 1992 for so many years. If you were to go back in time, would you start it differently or would you just follow the same?
No, I think I started this work in 1995 after I joined the IOE. So I mean, my PhD thesis is a dynamics vibration control for CMM. And I'm really dynamics control person. It's not whatever I talk about. So I started working on this one. Really in 1995, I moved to IOE. I cannot do dynamics vibration control. So I started work on this. So in my opinion, okay, I'm not sure if, okay. That's really honest, my opinion. Not something you planned. Something there's the opportunity, and you identify this opportunity had potential impact. Do your best, do our best to use my strengths to solve this kind of problem. And also you can see all this research results, methods, somehow related with automatic control, signal processing, and optimization. This is really my training in EE before, in the past. So when we work on research problems, my opinion, I ask my PhD students always the same question like this. Is this problem really important problem? Is this problem really new? Or you try to improve others' methods? That's okay. So the first, is this really problem? Second, why you? Why you can do it? If you, what you have, I mean the background training, what you don't have, how can you prepare you to work on this? I think these two questions are important if I look back. So I think really, for the problem I'm doing, I try to work on the real problem nobody can solve in the moment. And then I think what I try to learn to solve it, or my students learn.
I think you have done extraordinarily well, and then whatever you have done, started this whole field and then helped the whole community. Congratulations.
Oh, thank you, thank you.
In terms of the recent trends and interesting inspection or assessments or control actuation technologies in manufacturing, is there anything that particularly interests you now and the direction you can see yourself going?
I can see the need. Again, just like I said before, there's a need, but I'm not sure I'm the right person. Maybe you are the right person to do it. So I just say a few words, a few of them. So I think when Haoyan started the PhD topic 10 years ago, 8 years ago, I told him, I said, you should work on high-dimensional video signal monitoring because it's become cheaper and everywhere, okay? So it's that time. So right now it's really hard, but you say 10 years ago, not so hard yet. So right now, I would say something heterogeneous data, image as a response. So I change something, the image is changing. The image is changing, performance. These are really important topics. And that's one image. Another one is multi-signals. I call this coexist. I have students work on this one. Should I say it? So something, we study correlation. We study correlation, right? These 4 fingers correlated. You can use a linear correlation. And if something happened, I don't say, okay. I don't say throw a bomb in the middle of the classroom. But something, okay, I punch the table very hard. People get scared. So the people outside run out. And these people may be shot. And another person do something. So you can see all these things driven by one thing. All these things have functional curves all over the places. Sorry. I gave a name called the coexist. I mean, not correlation, coexist. These kind of things is distance measure or something, but this kind of thing is very important. Yesterday, Professor Tang asked a question about the image from the root causes. I mean, in another workshop, how to do it. I think if we can solve these coexist problems, many things can, cannot be solved. Cannot say solved, but will be have better solutions. I mean, cloud data is another one. I mean, data cloud is cheaper, very, very cheap right now, but how to do it? I mean, I can keep talking problems, but not solutions.
For the sake of timing, let's thank Professor